Lacerna's webinar on mass spectrometry and its applications in clinical research. I'd also would like to thank Dr. Gladys Completo and of course Dr. March Peña for spearheading many of these webinars for August and also for the coming months. For those who have not been familiar with PAASE, PAASE is a 42-year-old organization of scientists and engineers of Filipino descent, started in 1980 in the state of Indiana at Purdue University, and it has grown into more than 500 strong scientists and engineers who are pursuing research and teaching in various places around the world. So magandang umaga po sa inyong lahat, and please enjoy this webinar this morning, and I hope that we'll have an engaging discussion after the lecture of Dr. Lacerna. Salamat, Rap.
All right. Thank you po, Dr. Santo Domingo, for that welcome remarks. So before we begin, let me briefly introduce our speaker. Dr. Ana Karen C. Lacerna is currently an academic service faculty and equipment specialist of the chromatography laboratory at the Central Instrumentation Facility of De La Salle University in its Laguna campus. So prior to working as an ASF at DLSU, she was hosted by the same facility, CIF, as a DOST PCHRD Balik scientist, serving as a mentor in their Tuklas Lunas Fellowship Program, as well as a lecturer in food analysis and providing guidance in administrative, technical, and research activities at CIF. So Dr. Lacerna earned her BS Chemistry degree from the University of the Philippines, Los Baños, under a DOST SEI scholarship, and graduated magna cum laude in 2005. And after a few years of working at the quality assurance, as a quality assurance officer at Mead Johnson Nutrition Philippines, she pursued her PhD in chemistry at NUS, and her dissertation was on metabolomic studies of trauma injuries. So without further ado, let's all give a warm welcome to Dr. Karen Lacerna. So stop share.
Okay.
All right, so let me see. Okay, so you can now share, Karen.
Okay, yeah. So thank you, Rap, for that kind introduction. Magandang umaga po sa inyong lahat. For those who are here in the Philippines, for those who are abroad, magandang hapon or magandang gabi po sa inyo. So let me just share my screen. So again, I'm Dr. Karen Lacerna from the De La Salle University Central Instrumentation Facility. And today I will be presenting to you about mass spectrometry and its applications in clinical research. So for the agenda, we will be discussing on first, an introduction to mass spectrometry. I will be giving an overview of mass spectrometry. What is it about? And then go into the applications of mass spectrometry in clinical research, and subsequently discuss future perspectives in terms of the application of mass spectrometry in the clinic. And later on, I will also provide an overview of our facility at the De La Salle University Central Instrumentation Facility.
Wow.
Okay, so for the first part, I'll provide introduction to mass spectrometry. So when we talk about mass spectrometry, this is a technique that was first devised by Sir J.J. Thomson, who is also well known for his discovery of the electron, when he tried to separate particles of different masses using a particle beam and determine their relative quantities. So this is an important technique that was established for in a way, it weighs ions. You're looking at the weighing of ions in gas phase, either for atoms or for molecules. So basically, this involves the motion of these ions through an electric or magnetic field. So they are separated based on mass to charge ratios. And the applications can be for molecular weight determination, for structural characterization, gas phase reactivity studies, and for qualitative or quantitative analysis of components in a mixture. So just to give you an analogy, if you have your light source and then you pass it through a prism, you will see the spectrum of colors, right? So similarly, for mass spectrometry, if you have an ion source through which the analytes has passed through, your mass analyzer, which is part of the mass spectrometer, will actually separate those ions out, producing your spectra. Then in terms of the instrumentation, you would have different major components of the mass spectrometer. So first, you would have your sample source. This can be direct injection of your sample to the mass spectrometer or through flow injection, wherein you make use of separation techniques like liquid chromatography, gas chromatography, or capillary electrophoresis to introduce your samples to the mass spectrometer. So then it will go to the inlet that allows you to introduce the samples into the MS system, and then you have your ion source. So the ion source produces the ions from the samples. So in mass spectrometer, the main requirement for the analytes to be detected is that they should be ionizable. So your ions will be produced in the ion source. Next will be the mass analyzer. So it is in the mass analyzers that you separate ions out based on their mass to charge ratio. These can be through the application of a magnetic field or by the application of an electric field. Then you would have your detector. So the detectors will count the ions that are produced, and this will result into the creation of your spectra. You would have your instrument control and data system that will control the instrument, process the data, and that is generated from the detector and produce the mass spectra. So these parts, so your source plus the mass analyzer and detector, will be in a vacuum system. So currently we have ion sources that are not part of the vacuum system already. It is mainly the mass analyzer and the detector that is part of the vacuum system. So this vacuum system is important to ensure that you minimize ion molecule reactions, scattering, and the neutralization of the ions. So in terms of sample introduction, again, you can either have direct insertion of your samples into the ion source of your mass spectrometer, or it can be through direct infusion. So in direct insertion, you put the sample in a probe, and this is directly introduced to the ion source. There will usually be a vacuum interlock that is employed, and vaporization and ionization will occur through thermal desorption as well as high energy desorption, or for example, your laser desorption. Now for direct infusion, so from the word infuse, you would have flow of your mobile phase, be it gas or liquid, that will introduce your samples into the ion source. So you would have your GC, LC, or CE for this part. And usually for this part, you do not need the vacuum interlock anymore. And in some cases, well, this will be in atmospheric conditions and ambient conditions. So in terms of ion source, so in mass spectrometry, the different configuration of mass spectrometers can be mainly defined by its ion source as well as by its mass analyzer. So in terms of ion source, you would have different ion source for different types of application. So electron ionization is mainly used for gas chromatography. So if you're coupling your GC with your mass spectrometer, then electron ionization is the most commonly used ionization mode. So here you would have your filament and your trap. There will be electrons passing through it. You would have a gas stream containing your analytes from the GC. And then there will be a collision of your analytes with the electrons that are passing through orthogonally or perpendicularly, and then from there you will create your ions that comprises your molecular ions as well as your fragment ions, and these will then be subjected for MS analysis. Now in electron ionization, this is a highly reproducible ionization mode, and if you apply ionization at 70 electron volts, actually you can make use of the spectral library or the spectra that you generate for purposes of identification of your compounds. So different compounds will have different fragmentation patterns produced when they are subjected to this ionization, and these can be used for identification. So for example, you have your NIST library that you can use for the spectral library matching of your compounds of interest. Okay. So for the next part, you would also have chemical ionization. So in chemical ionization, this one is a soft ionization that produces ions of little excess energy. So in ionization modes, you would have your hard ionization, which creates a lot of fragments, and you have your soft ionization modes, which creates less fragment and more of your molecular ion. So in electron ionization, that will be more of a hard ionization technique. Chemical ionization will be your soft ionization technique. So for this one, you you introduce reaction gases as well, aside from the analytes, and these will collide with your analytes, producing your protonated ions. So in positive mode, you have your protonated ions. For negative mode, you have your deprotonated ions, and these will then be subjected for analysis. So if you compare your electron impact or electron ionization and chemical ionization spectra, here in the electron ionization spectra, you produce more of your fragment ions, none of your molecular ion. In CIMS or chemical ionization MS, you produce more of your molecular ion and less of your fragments. You would also have your fast atom bombardment ionization, wherein you dissolve your samples in a liquid matrix, and then you use high energy atoms to sputter the ions from your sample, and from there have it detected in the mass spectrometer. So in fast atom beam, this is usually used for thermally labeled samples because with this one, you do not require any heating. You also have your matrix-assisted laser desorption ionization mode. So this one is this was actually invented by Koichi Tanaka, for which he won a Nobel Prize in 2002. And this is because this allowed for the detection of macromolecules or biological macromolecules like your oligonucleotides, peptides, and proteins. And in this one, your sample is mixed with a solid matrix that absorbs at a laser radiation wavelength of a particular laser radiation wavelength. And then from there, you produce your ions. And by using the matrix, you help minimize the damage to the sample. And for this, it is considered to be a soft ionization technique because you form more of your molecular ions and few of your fragment ions. So again, this is usually used for proteins and other biological macromolecules. You also have your secondary ion mass spectrometry or secondary ion ionization mode. This is also similar to fast atom bombardment, but the difference is you do not use a matrix, and you make use of high energy ionizing beams. So you have a primary ionizing beam that that bombards your sample, and then from there you produce your secondary ions. So this is used for studies of surface chemistry, creating high resolution chemical maps that can be used for surface and depth profiling. Now, secondary SIM and FAB and MALDI usually happens with your samples put in a vacuum interlock. Subsequently, when your coupling with LC and GC came in, then you would need something that will be more suitable for coupling with these equipments as well. So atmospheric pressure ionization modes have been have been subsequently developed, and this involves the introduction of your system through pumps or syringes, such as what you have for your GC, CE, or LC. So you would have a heated transfer tube that will allow you to introduce your samples into the heated ion source of your mass spectrometer. And then you would have differential staged pumps that is decreasing the pressure through the system. Initially, you would have your system at about 1 torr, subsequently at 10 to the -3 or 10 to the -5 torr, and then subsequently at the last part where you have your mass analyzer, you would have your mass spectrometer at 10 to the -5 or 10 to the -7 torr. So this is a useful ionization mode for thermally labeled samples, and this allows ease of coupling with your HPLC and CE techniques. Electrospray ionization was first devised by John Fenn, for which he was also one of the winners of the Nobel Prize in 2002. This is a very soft mode of ionization. Sorry. Okay, so can I ask? Okay, thank you. So for the electrospray ionization mode, you have your sample with your mobile phase that is introduced through a spraying nozzle. You create fine mists of droplets that are charged by passing through this Taylor cone that is charged. So depending on the mode of ionization that you want, whether positive or a negative ionization mode, a similar charge will be imposed on the droplets. So from there, you would have charged droplets, and then when the solvent evaporates, the charges around the droplets will come closer into contact with one another, and this will cause repulsion, and this will lead to what is known as Coulombic fission or Coulombic explosion. And then from there, you produce your charged analytes that will enter your mass spectrometer system. Atmospheric pressure chemical ionization would be similar to the chemical ionization. It will be similar to the chemical ionization in that is used for gas chromatography, wherein you also introduce some reaction gases. But in terms of like comparison of your ESI and APCI, the difference is for APCI, you first dry your analyte droplets before it's subjected to ionization. In APCI, in ESI, you first put or introduce the charge to your droplets before they are evaporated. So mainly, APCI is more applicable for relatively more nonpolar and smaller molecules as compared to your ESI. So in terms of choice of ionization techniques, you have your EI and CI for neutral to polar compounds, and this is mainly applicable for GCMS. For LCMS, you have your APPI, APCI, and ESI. Your APPI and APCI will be more applicable for your neutral to polar compounds. For ESI, it can be applicable to neutral to ionic compounds, and it can cover from very small to high molecular mass compounds. MALDI is mainly applicable for compounds that are of high molecular mass, such as those that are 10 to the 3 and up in terms of AMU or Dalton. So in terms of applicability, it will be the ESI that will be most applicable for a wider range of compounds. So it can cover both small molecules as well as your larger molecules. Now, in the recent decades, ambient ionization has been developing. So if previously you have your sample preparation involving several hours, and then subsequently subjecting them to GC/LC analysis, now you have techniques that involves ambient ionization, wherein the ionization will happen directly in open air conditions, requiring no pretreatment. So it allows direct sample analysis and then give you a mass spectra. So In terms of differences, of course, you would have the added advantage of like separating out your compounds first in GC and LC before they are detected. But in terms of the speed of analysis, you would see like how fast ambient ionization MS will provide you results that you can use. So some examples of ambient ionization techniques that are currently available will be your paper spray ionization. So for example, if you have a dried blood spot, and then you put some solvents in, put some gas that will allow for your analytes to flow from your paper to the mass spectrometer inlet. And then you would also have your rapid evaporative ionization, MS, or REIMS, or REIMS, wherein it can be applied directly on the tissue samples. It can be done in the surgical table, and you can get a profile of like the tissue samples directly at the surgical table. You evaporate some of your analytes, and then it goes into your mass spectrometer system. You would also have your direct analysis in real time, or DART, wherein you introduce your sample. It can be a tissue sample or some sample that is on the tip of a pipette tip, or also in a paper system like the one you have for paper spray ionization. You introduce your sample in the sample gap. You allow, you have your electrode here, and you have some gas that is flowing through, and then your analytes will then go into your orifice. You would also have direct electron spray ionization. This is similar to your ESI. The difference is it's direct on the sample, so you're not subjecting it to chromatography or electrophoretic separation anymore. Rather, you would have a gas jet that has solvent. Then this solvent spray will hit your sample, and this will cause the desorption of your ions that will go into your mass spectrometer. So these are more relatively newer ionization techniques that are being employed. And again, your advantage is it can be done in open air conditions. Now, the second part that is important in terms of the mass spectrometer, and actually this will be the part that will determine the name of your mass spectrometer, will be your mass analyzer. So for the mass analyzer, once the ions are formed, they are separated in the mass analyzer. So the mass analyzers will be the one responsible for separating the ions according to their mass to charge ratio, and also for filtering the ions. So you, in mass spectrometer, you define the range of mass that you want to detect. And so this will be at this part that the filtering will occur. So you have two types of mass analyzers. So you would have those that are continuous. So the ions are continuously flowing through your mass analyzer, such as in the quadrupole and magnetic sector. You would also have those that are pulsed analyzer, wherein there will be time segments wherein you collect your ions and then subject it to detection and so forth. So some important terms to remember in mass spectrometer. So resolving power, so you're referring to the ability of the mass spectrometer to separate your adjacent ions. This mass resolution is your measure of resolving power, and this can be calculated by this formula, wherein you take your peak mass in Daltons and divide it by the full width at half maximum. And you can see here, so if you have a low resolution mass analyzer like a quadrupole, you would have a very wide peak with a wide FWHM. If you have high resolution MS, you would have high resolving power, and you would have very sharp peaks. So in terms of mass error and mass accuracy, so mass error will provide you with a measure of the accuracy of the mass information, and this can be calculated using this formula, wherein you take your theoretical mass minus the measured mass. Mass accuracy can also be calculated using the mass error divided by the theoretical mass multiplied by 10⁶. You would also have to take note of the term monotopic mass. So basically, this is the mass that is based on the on the atoms of the highest abundance. So this is also known as your exact mass. So for example, if you have your C6H12O6, then your carbon will be based on the carbon 12, your hydrogen will be based on the proton, and your oxygen will be based on oxygen 16. In terms of like the quadruple analyzers, we'll briefly go through the different types of analyzers that are employed. So you would have your quadruple analyzer, wherein you have, from the term quadruple, so you have 4 poles, wherein you have alternating applications of your direct current as well as your radio frequency. And based on these applications of direct current and radio frequency, some ions will go through the mass analyzer, and some will be hitting the walls of your poles. So this allows you to filter your ions based on your defined mass to charge ranges. You would also have your magnetic sector. So this is considered to be the most expensive mass spectrometer system. They are usually also the biggest in terms of like the footprint that you have in terms of the mass analyzers. So basically here, what is applied is the magnetic field. So in the application of your magnetic field, and you have an arced mass analyzer, some of your ions that are that are of, depending on their acceleration, some of them will hit the walls of your magnetic sector, some will hit some will enter the mass spectrometer system. So this is based on what is the applied magnetic field strength. So some in this way, they're also filtering the ions that will enter the mass spectrometer. In terms of time of flight analyzer, so the ions are accelerated through a flight tube by the application of an electric field. So if you consider your ions here, the smaller ions will reach the detector faster. Your larger ions will reach your detector slower. So with that, you are able to separate out your different ions. You would usually have a reflectron. You would usually have a reflectron here that allows you to increase the flight tube or the length of the flight tube. And by increasing further the length of the flight tube, you are able to separate out your ions better. Ion trap analyzer would, from the term itself, it allows you to trap your ions, and then depending on what you want to do, you can trap them and subject them for detection, or you can trap them, select like a particular ion, and then subject it to fragmentation, and from there do MSN or multiple MS stages prior to detection. So in ion trap, you have your ring electrodes. Applications of potential will then trigger the trapping of your ions, and then based on what you want to select, you can release the rest of the ions, select a particular ion, subject it to fragmentation, and then from there, again, you can do multiple stages of fragmentation. Ultra high resolution MS systems will include your Orbitrap, wherein you have your C-trap, where the ions are oscillating, and by the oscillation of these ions through the C-trap allows you to generate allows you to get that separation of ions. So Orbitrap is actually considered to be the one that is of highest resolution. You would also have your Fourier transform ion cyclotron resonance, and this is a separation of your ions based on the cyclotron frequency of the ions that is in a fixed magnetic field. So in terms of the comparison of your mass analyzers, you would have quadruple that is of low resolution, but this is actually the one that has fast scan rate. In terms of like, it gives you the ability to do tandem mass spectrometry. So if you have a triple quadruple system where you have a quadruple, a collision cell, and a second quadruple, then you can do tandem mass spectrometry. You also have your ion trap. This one, sorry, can we move? Can we mute that? Okay, thank you. So for ion trap, you can do MSN fragmentation. And of course, you would have your high resolution and ultra high resolution systems that you use to get accurate mass information for your identification of compounds. And some of these can be coupled with the quadrupole, or in by itself, they can do tandem mass spectrometry, wherein you get your fragment and use that for structural elucidation. So detector, basically this will allow you to detect the ions that are coming from your mass analyzer, and then that will allow you to create your signals that will appear in your mass spectra. So vacuum system, again, is needed to ensure that you prevent ions from colliding with the other molecules or ions, and this is usually of multiple stages. So in tandem mass spectrometry, so you have an initial mass analyzer that selects a parent ion or precursor ion, and then you subject it to collision with a particular collision gas, and then you produce your product ions that are then transported to the second mass analyzer. So this can be tandem in space or tandem in time. So if when you say MSMS, you are looking at experiments performed using tandem instruments. Product ions will be the fragment ions. Parent ions or the precursor ion is the one that is selected by the initial mass analyzer for collision-induced dissociation. So an example of tandem MS in space is a triple quadrupole. So you would have your first quadrupole to select your parent ion or precursor ion. You have the collision cell wherein the collision-induced dissociation occurs. And then you have a second mass analyzer that allows you to select, that will allow you to select the fragment ion of interest for detection. So this is just to illustrate that concept of like initial selection of ion, fragmentation, and then either you allow all the ions to pass through or you select certain ions for the second mass analyzer. Tandem MS in time can be demonstrated with the use of an ion trap. So first, in the same area, so if tandem in space, the fragmentation occurs in a different region of the mass spectrometer. In tandem MS in time, everything occurs in the same region or in the same part of your mass spectrometer or mass analyzer, but at different times. So first, you would have your ion accumulation. You select a particular ion that you want to fragment. You subject it to fragmentation, and then you select a particular ion to detect. So again, this can be done for multiple stages, allowing you to get MSN information. So advantages and disadvantages of tandem MS. Of course, you attain the chemical specificity. You do not need so much in some cases wherein you cannot really resolve the peaks chromatographically. The use of a tandem MS will allow you to get some specificity. The information that you get can be used for structural elucidation. You reduce the analysis times because, again, you do not need to separate everything so much. And then you would have your increase in sensitivity through noise reduction. You reduce the chemical background by selecting the ions of interest. And this can be used for screening. So if you want to select neutral loss scans, this can allow you to select only certain classes of a particular molecule or class of molecule. Disadvantages will be, of course, they tend to be expensive. The interpretation of spectra might be difficult, and then complexity of the instrumentation as well as the resulting spectra. In terms of MS acquisition modes, if you have a single mass analyzer, you can do scanning. So that means you allow all the ions to pass through. They are just separated based on their mass to charge ratios. You can also select a particular ion for detection. In tandem MS, tandem in space MSMS, you can do product ion scan wherein you fragment a particular precursor ion and subject all of its fragments for detection. Selected reaction monitoring or multiple reaction monitoring, you select a particular parent ion, fragment it, and only select specific daughter ions or fragment ions. And this allows you higher specificity of detection. Then you would also have your neutral loss scan, wherein you detect only the ions that produce a particular loss of a certain mass. And then you have your precursor ion scan that allows you to detect only the analytes that produce a particular fragment. So in terms of, so as I mentioned earlier, mass spectrometry can be coupled with MS. So compared to hyphenation with other detectors, coupling with MS provides higher sensitivity and specificity, more definitive information on your mass and structure. And usually you would have your HPLC or GC that is coupled with your mass spectrometer system. So then you obtain an additional dimension of components. So for example, here's an example of your HPLC DAD or diode array detector chromatogram. So you generate a three-dimensional plot as you scan through different wavelengths of absorbance. But the problem is you cannot identify the different components based without standards. So you would have to have the standards for these different compounds to be able to say which one is which. For mass spectrometry, aside from the chromatographic separation, you generate mass information. And from this mass information, you will be able to have like some information that you can use for the purpose of identification. So in terms of hyphenation of LC with MS, so this can be used to analyze a diverse range of molecules that are usually of the non-volatile and thermally labile, and they can be used for high molecular weights and of differing polarities. So the main condition is that your mobile phase, the additives, as well as your samples can be they are volatile and can be ionized. Your analytes can be ionized. For GC hyphenation with MS, so since your analytes are already in the gaseous phase, there is a more direct transfer of your analytes from the GC to your mass spectrometry system. So the requirements for this is that your analytes must be volatile, they must be thermally stable and ionizable. So in terms of the requirement for interfacing, so there should be an efficient transport of effluent from GC to MS, because in GC, you produce very narrow peaks, so they elute out very fast. And so there should be an efficient transport going to your MS. And the analytes must not condense in the interface, so you would usually have a heated transfer line from your GC to your MS, and the analytes must not decompose before entering your ion source. And the gas load must be within the pumping capacity of your MS. So in the coupling of your chromatography with your mass spectrometry system, you can have analysis in the untargeted mode. And this is usually performed as an exploratory analysis. And this is usually done with a high resolution MS coupled to your mass spectrometer. This is usually done with a high resolution MS coupled with your chromatographic system. And scan mode is employed. For targeted analysis, you analyze known compounds or classes of compounds. You make use of tandem mass spectrometry, and acquisition modes is mainly the main examples will be multiple reaction monitoring or the use of precursor, product, or neutral loss scans. Okay. So in untargeted, you get a whole fingerprint like this. Whereas in targeted, you look at specific compounds of interest. So in our facility in CIF, we have a UHPLC QTOF that is an LC-MS system, LC Tandem MS system, as well as a GC coupled with a mass selective detector or a quadruple MS that has ability for headspace sampling and liquid injection. So these are the two systems that we have at CIF. So again, mass spectrometry is not only applied for molecules, but they can also be applied for elemental analysis or to detect your atoms. So usually this is done using inductively coupled plasma. So plasma is the fourth state of matter, and this is produced as the ionized gases are formed through the application of with the application of an electromagnetic coil. So the ions produced are mainly singly charged, and then these can be coupled with detection systems like atomic emission spectroscopy, optical emission spectroscopy, or mass spectrometry. In terms of detection limits, ICP-MS will be providing you with the highest sensitivity in terms of detection. This will be the schematics of your ICP-MS. So you have your sample introduced into this plasma torch. You have argon that is flowing in. So this is from this argon gas that plasma will be produced. And this will allow also the creation of your ions that are singly charged from your elements that are present in your sample. And then they will be subjected to detection using a mass spectrometer system. Now, we also have an ICP-MS system at CIF. This is still currently in work. So this is still for further validation. And later on, we'll update you once this is operational. So this can be used for the simultaneous trace level analysis of multiple elements and for analysis of heavy metals. So the next part is to discuss the applications of MS in clinical research. So MS in clinical research can be applied for purposes of pharmacokinetics and to determine the modes of action of your pharmaceuticals. It can be used for biomarker discovery, for diagnostic and theranostic purposes. So diagnostic is for like for determination or detection of certain diseases. Theranostics is more for like to accompany your therapies, or if you're taking certain drugs, if you want to detect or determine how that particular drug is affecting the patient, then this can also be used for that purpose. It's also used for studies of disease mechanisms, identification of microorganisms, as well as for imaging. So actually, this biomarker discovery, studies of disease mechanisms, as well as the pharmacokinetic and modes of pharmacokinetics and modes of action, they can also be parts of the application of mass spectrometry in omics technologies. So application of mass spectrometry in pharmacokinetic studies, usually multiple reaction monitoring is used, wherein you try to detect compounds of interest, like for example your drugs, using LCMS or LC Tandem MS, wherein you select a particular precursor ion that is corresponding to your drug, fragment it, and then select corresponding fragment ion. And this will allow you to obtain high sensitivity. You remove much of the noise, and this allows detection of your compounds of interest. So here you can see you have an LOQ of 0.01 nanograms per mil, and you can detect levels of your compounds at nanogram per mil levels. Another application of mass spectrometry that is quite popular will be in newborn screening. So you would have different metabolic disorders, and they would have certain biomarkers that will be either elevated or depleted in the presence of certain of these metabolic disorders. And this is just an example of an application wherein you have your dried urine, urine that is placed on filter paper that is dried, and then you can subject it to extraction using ammonium hydroxide and use flow injection for detection. And also a second-tier analysis is done using HPLC, Tandem MS, wherein you detect you use multiple reaction monitoring to detect your analytes of interest that can later on be used to identify your metabolic disorders. MS-based techniques is also widely used in omics applications. So omics technologies allows you to study your biological systems at different molecular levels, be it in the genomic level, in the transcriptomic level, in the proteomic level, as well as in glycomic, metabolomic, and lipidomic levels. To add to this, you can also look at the metalomic profile or the elemental, the trace elements profile of your samples. So in MS-based techniques, it can be used for genomics in terms of mass spectrometry-based genotyping. It is widely used in proteomics for proteomic and phosphoproteomic profiling, as well as in glycomics. So glycomics looks at the glycosylation of your protein. So this is a post-translational modification, and this can be used to study that as well. Metabolomics will be to profile your metabolites. So this metabolomics is actually looking at your metabolites that are closest to the phenotype in terms of the different molecular levels. And this, as you have seen from the newborn screening, these metabolites can be associated with certain disorders or diseases. And also, you would also have a spin-off of the metabolomic technologies will be your lipidomics. So this will be looking at your lipids, and this can also be used for profiling your diseases or studying their disease mechanisms, etc. MS-based techniques have been widely used also in recent times due to the in studying your SARS-CoV-2 virus as well as in COVID-19 research. So not only is it used for studying your virus, but also looking at different biological fluids obtained from healthy, asymptomatic, mild infected, severe infected, and recovering individuals, and then they can be profiled using your different omic levels. And from there, you'll be able to determine what are the possible biomarkers of the disease. This is some pictures from Grey's Anatomy. So just to show you like how it's getting into the popular, it's getting into the media, like the application of mass spectrometry. So you have here Richard Weber showing this this device that is allowing the detection of cancerous cells in the tissue samples that are used here. Now he calls this the PathPen. This is actually inspired by an innovation by Zhang and his co-workers that is using handheld mass spectrometry for the non-destructive tissue analysis that will allow you cancer diagnosis. So basically in this system, you would have like your mass spectrometer, and this is integrated with the handheld device. The handheld device has a 3D printed tip wherein water is flowing through one side. This will come into contact with your sample. Then subsequently, analytes that are collected in the water droplet will be suctioned through vacuum into your mass spectrometry. And here they show like how they were able to distinguish normal thyroid tissue versus papillary thyroid tissue carcinoma carcinoma section. And you can observe the detection of certain lipids or phospholipids that are either elevated or depleted in your carcinoma tissue section. MALDI-TOF MS is also widely used in clinical microbiology for the determination of identity of your bacteria as well as your fungi. Basically, what happens is you can have your different specimen. Either you can subject them for culture and then subsequently use the direct smear as the target for MALDI MS analysis, and you will get your spectra that can be compared with the databases that are available. Or you can subject them to extraction and also use them as multi-targets. For this, you can do identification of your different microorganisms or microbes. It can also be used to detect antibiotic resistant strains through certain changes in their lipid profile. Mass spectrometry can also be used for imaging. So here you see like certain biomarker ions for oleic acid, arachidonic acid, phosphoserines, and phosphatidyl inositols that are detected using MAL-DMS. Basically, you can see the images of the imaging of these different ions and how they are showing how they are present or depleted in pancreatic cancer cells. Here, they are looking at the distribution of the drug paclitaxel in tissue section. So again, this is more of an application of trying to determine the distribution of drugs in tissue samples after the intake of the patient. So here you are able to see the levels of paclitaxel in the different samples. So that's it for the presentation of the mass spectrometry and the clinical applications. I would like to briefly introduce you to our facilities. First, future perspective for clinical applications. So, of course, the desire is to bring mass spectrometry technologies further closer to the bedside or to the surgical table. In order for this to happen, you need to make sure that you have established validated biomarkers. So currently, there's a lot of study going on in terms of identifying biomarkers for different diseases. But of course, this has to be validated using large cohorts and possibly through across different races. Because of course, in terms of for example, for metabolomics, the metabolomic profile can be capturing your environmental factors, your dietary and nutritional factors, and this has also to be correlated with what is being seen in terms of the differences between your disease and your healthy samples. It has to be quantitative. They have to have, currently, you have a lot of untargeted studies that are looking into these biomarkers, but eventually they have to be quantitated properly so that you have your levels that you can look into in terms of detection of, okay, are the levels acceptable for healthy or are they already indicating disease? Of course, it will be important to standardize your method for application across different applications. And it will be good to have simpler and more robust instrumentation that will allow these high-end, this massive, sometimes massive instruments to be brought closer to your bedside, and something that will be more approachable for those that are in the clinics or in the clinical in clinical research, as well as to those who are in the hospitals. So again, now I'll provide just a brief overview of our facility. So we are at Laguna campus of De La Salle University. So this is located in Binyan, Laguna. So we serve the research needs of the country, not only for those who are in La Salle, but also across the country. So we serve both internal as well as external clients. So we offer analysis, trainings, consultations, collaborations, and research outsourcing. So for your analytical requirements, we have different laboratories. So we have a 600 megahertz NMR at the NMR lab. We have a range of spectroscopy instruments at the spectroscopy lab. The chromatography lab, which I'm part of, has a QTOF LCMS, an analytical HPLC, as well as semi-prep HPLC and GCMS. We have electron microscope, SEM and TEM, as well as FIB in our integrated electron microscopy lab. Currently, in ongoing establishment is our imaging and cell culture lab, or ICEL, that has a confocal laser scanning microscope, as well as genetic workstation and cell culture facilities. And later on, we will also have the wind tunnel testing laboratory. We also have a range of other equipments that are available for sample preparation and analysis. So you can follow us in our Facebook page, www.facebook.com/DLSU-CIF. We have a range of webinars available in our YouTube channel. And again, if you have inquiries or if you would like to inquire about service analysis or collaborations, please do email us at ciaf@dlsu.edu.ph. And that's all, folks. So these will be my contact details if you need any further information. So thank you, PAASE, for this opportunity, and thank you very much to all of our participants today.
Okay, so thank you very much, Karen, for that very informative talk. And I'm sure a lot of, or many of our attendees here today learned a lot from you. Before we go to the question and answer part, let me just briefly welcome Dr. Gisela Concepcion, the former president of PAASE. Good morning, Dr. Concepcion.
Good morning.
Good morning po.
Hi, good morning po. So, so if you have questions, comments, or clarifications to Dr. Lacerna, kindly raise your hand or type it directly in the chat box if you don't want to personally ask it to Karen. So, any questions from the audience? None. So maybe
There's one in
okay.
There is a question in the chat.
It's in the chat. Yeah.
Okay, sorry. Yeah, so this is from Jaja. Yeah. So Maria Jamaica. All right. So her question is, I'd like to ask if you have already performed quantification in your HPLC QTOF mass spec using TOF MRM, and if yes, could you share with us a simple workflow on how to go about it?
Okay. First of all, QTOF, you cannot perform multiple reaction monitoring because the TOF part, so you can select a precursor ion or parent ion in the quadrupole, which is the first part of your QTOF system, but the TOF part will only separate your ions out. It will not have a filtering capability. So you cannot do MRM in your QTOF. So the most that you can do is do product ion scan. So if you have a particular analyte of interest, you can do a product ion scan, and then subsequently you can use that for obtaining your electron ion chromatograph, your EIC, or yeah, you can just do a scan analysis and then make use of the electron EIC or your extracted ion chromatogram for the purpose of getting the integration for your peaks. So in terms of like sensitivity, then yeah, that will be a difference between your QTOF as well as your triple quadruple or a QTrap that has that filtering capability. For QTOF, you cannot filter, you cannot do filtering, you cannot do MRM. You can just like select those high resolution mass to charge ratios for the purpose of your quantitation. So yun. I hope that answers your question, Yeah.
Right. So thank you, Karen. We have another one from Richard Arceo. Would you like to ask it yourself, Richard, or you want me to read it? You can. Richard, wala. Sige, babasahin ko na lang.
You may read the question for me, please.
Okay. So, Mr. Arceo is asking how useful would MS-based techniques in omics application be 5 to 10 years from now? So,
Okay.
future perspectives.
Yeah, so I think it will continue to be a relevant technique. It is actually as long as there are diseases to study, as long as there are, because the thing is, it's not only applicable in the clinical aspects, it's also applicable in terms of like analyzing your food samples, in forensics, in environmental analyses. It's applicable in a wide range of applications. So it will continue to be relevant in terms of like the different applications looking 5 to 10 years from now, as long as there are diseases to study, as long as in some cases, if you're looking at pollutants, right now there's a lot of emerging pollutants coming in, and how does they affect people, how do they affect the body, then there are things that we can also still look into moving forward. Now, what would be interesting to look into 5 to 10 years from now is how do these technologies evolve through time? Like, as I mentioned earlier, can we bring these mass spectrometers closer to the bedside, or can we bring these mass spectrometer systems closer to the surgical table? And that will actually something that would, I think, be more relevant moving forward, especially once you've already have an established set of biomarkers. The next thing will be more to focus on the targeted analysis of these biomarkers. And for that, mass spectrometer system would still remain to be a reliable and relevant technology to use.
Thank you very much.
All right, so thank you, Mr. Arceo. So, siguro in the interest of time, we can have the last two questions here at the chat box. So the first one is from Ms. Tulin. Okay, see, Dr. Concepcion would have also a question. So, sige, so before we go to Ms. Tulin, sige po, Dr. Concepcion, you have the floor.
Thank you for accommodating my question. I'm sorry I came late. But Karen, Dr. Lacerna, congratulations. We use mass spec a lot for our research on cono-D and peptides, which are disulfide linked. So we may get the primary sequence of the peptide, but there are several types of scaffolds, disulfide scaffolds. Although we have a hypothesis of how the disulfides are connected in the small peptide. So, well, mass spec is very powerful in the sense that it's sensitive and requires very little material, but it's always useful to combine it with the chemical methods to process the, say, the material, the peptide, before subjecting it to mass spec. In our case, we would have to find a way to break the disulfides, okay, with proper reagents for reduction and then alkylation. So there's a reduction alkylation process before subjecting it to mass spec. So and fragmentation. So I just want to know if you and the DLSU facility would have these kinds of expertise to well, help make the best use of your facilities, which are very impressive at this time. My second question has to do with the frontier of mass spec, which is being led by Dame Carol Robinson on the use of mass spec or the gas phase, precisely again to determine 3D structure of proteins. And I had the privilege of listening to her once in Academia Sinica, and she was discussing this, and it's electrospray based. And I'm just curious how far that area of mass spec applications have advanced. Because then again, a problem is always quantity, although many of the proteins of interest to us in the biomedical field, they can be synthesized and they can be biosynthesized. But on the other hand, for discovery, you may be able to first just get a little material. And so I think mass spec might potentially be a very powerful method, aside from the liquid phase of structural elucidation, which is NMR, and of course a solid phase of structural elucidation, which is a crystallography. So I'm sorry for the complex question, but I think these are two very important areas of application. Thank you.
Okay, thank you very much, Dr. Concepcion, for the two questions. In terms of our facility at De La Salle University, CIF, Currently, we mainly have the mass spectrometry system. In terms of the chemical modifications, the derivatizations that are for use for peptides, specifically for alkylation and, as you mentioned, for the breaking of your disulfide bridges. Currently, we do not have the reagents yet. But if you would be interested to submit samples for analysis, we can look into acquiring these reagents. In terms of the, aside from, I agree that mass spectrometry by just direct analysis will not be sufficient, especially if you are looking at isomers. You have similar molecular weights, then and almost similar fragmentation patterns. Then you wouldn't be able to distinguish your different compounds or your different peptides. That is where your chemical modification comes in. And also another technology that is applied in mass spectrometry that may help this part will be the use of ion mobility, wherein you measure cross-sectional areas of your, wherein you separate out ions based on their cross-sectional areas. And so perhaps because of how these disulfide bridges affect the shapes of your peptides, I would assume that this would be something useful for your application. In terms of like developments in proteomics or protein analysis using mass spectrometry, that one, I'm sorry, but I'm not as familiar. Mainly my applications are using or on metabolomics, glycomics, and other small molecule analysis. But from what I know in terms of proteomics or protein analysis, especially if you're dealing with very small quantities of sample or then you would need nano LC. So in nano LC, you make use of nanoliter per minute flow rates. Then you have less dilution of your samples. Then that will allow you to have higher sensitivities for detection. And currently, there's also, as I mentioned earlier, there are developments wherein you do not need to incorporate dilution through the chromatographic system. You can do MALDI analysis that allows direct ionization as well as your other ambient ionization techniques. So in terms of addressing issues with regards to the quantity of material that you have to start with, that might solve the issue. So I hope that I was able to answer your questions, Dr. Concepcion.
Right. Yeah. So thank you for the question, Dr. Concepcion, and
Thank you so much.
So Ma'am Gisela also had an additional note in the chat box. So yeah, so again, we can probably have this last question over here from Mr. Jason Alcano. So I heard about miniaturized MS systems. So he is asking whether or not these are comparable with the larger MS systems.
Okay, so for miniaturized MS systems, so in terms of their capabilities with regards to resolution and mass accuracy, there might be differences. One of the miniaturized systems available will be the Waters QDA, that is a single quadruple mass detector. It can mainly detect ions based on unit accuracy. So no decimal places, just the unit value of your mass to charge ratios. There is also, I think, some miniaturized TOF systems, but again, also there will be limitations in terms of the resolution as well as possibly the accuracy. So it's not as yeah, in terms of like the performance, in terms of resolution, mass accuracy, there will be differences. But of course, there is that prospect of getting these miniaturized systems more accessible in terms of like your clinical applications. So yeah.
Okay, so thanks, Karen. So the last question here is from Ms. Tulin. Sorry, I forgot. So she's asking what kind of samples have you already analyzed at CIF, I guess, and she's asking some papers related to this.
Okay. Okay, so yes, I'm not very sure again whether it's MRM or perhaps selected ion monitoring, because again, by virtue of the instrumentation, the TOF will not have that ability to filter out. But again, it would have the ability to allow you to get product ion scan, which later on will allow you to extract from the data your extracted ion chromatogram that can be used for your quantitation. So I'm not very sure about how the water Q-TOF system can do MRM, but by virtue of what I know about the instrumentation, it will be just selected ion monitoring or selected ion monitoring. So if you want to select a particular ion for detection. Okay, Raf, you're on mute.
Sorry, yeah. So thank you. So if you don't mind, I can type in the chat box your email address again for
Yes.
those who might have additional questions.
Yes.
Yeah. Okay, so you can email Karen anytime for your questions and clarifications. So it's already 18 past 10. So before, so again, thank you very much to Karen for these wonderful talks and the questions from our audience. And we're very happy that we have a very good attendance, 128 people. So hopefully you can also join the other two omics seminars that Rec 3 of PAASE is organizing. One would be for next week. The speaker would be Dr. Marali. And the other one would be on, if I remember it correctly, Ma'am Gladys on...
It will be on lipidomics.
Okay. Yes.
It's
So,
on
Dr.
lipidomics,
Peña
and
pala.
it will be from Dr. Oh, it's hard to pronounce her name, but she's a colleague of Diana Aga from University of Buffalo, and she will present her research on lipidomics and its role in disease and diagnostics and inflammation. Yeah.
Okay. So yeah. So thank you for
That's on
Dr.
August 19.
Peña on August 19.
Yes.
There. So
And
thank
then
you.
one more, sorry, Rap. One more is on August 26th,
26.
Dr. Marilan Balulong from UP Manila, who will be speaking on metagenomics.
All right. Yeah. So thank you po, Dr. Completo and Dr. Peña for those information. So let me just briefly share this certificate of appreciation to Karen. So sorry, medyo yeah, so hindi pa siya signed. Yeah, so the certificate is proudly presented to Ana Karen C. Lacerna for graciously sharing her expertise in her talk entitled Mass Spectrometry and its applications in clinical research during this PAASE webinar series organized by the Research Expertise Cluster Council for Molecular Developmental and Genetics, REC 3. So given this 5th day of August, it will be signed by me, Dr. Michael Velarde, and Dr. Maria Margaret O. Peña. So please again join in giving a warm of applause to Karen for the successful webinar. So maraming salamat, Karen. Now before yeah. So
maraming
before
salamat din, Rap and PAASE. Thank you.
Yep. So before we end, I'd like to kindly request Dr. Completo to give the closing remarks for today's session.
Okay, so thank you very much, Dr. Karen Lacerna, for that very comprehensive and informative webinar on mass spectrometry and its applications in clinical research. So we hope to hear more from you. So I would like to invite you to please present on the 42nd APAMS so that we can hear more details about your research projects. And also just to remind everyone, as Rap mentioned, we have this weekly webinar from PAASE. So let me just share the webinar on next week, okay? Although Rap already mentioned this. Okay, so here's this. So we started with a general overview of the use of mass spectrometry in clinical research. So now we will move on to genomics, since the topic is on omic science for this month. So our next speaker will be Dr. Benedict Moralit, who is the director of the DNA sequencing core facility at the Philippine Genome Center. So please, if you're interested in learning what are the activities that PGC have been doing that is related to SARS-CoV-2, please join us next week, August 12 at 8 a.m. You may register through this link or you can just scan this QR code. Okay, so this will be available. So Rap will be sharing this because thank you, Rap, for having such a wide network. This is really a very good attendance, and we would like to see more of you in all of our webinars. So, and if you would like to have a certificate to be given to you, please send us an email. But you have to answer a survey form first before we send you the certificate. Again, thank you very much. We welcome you all. Please, I just don't have, wait, hold on.
Dr. Completo, if you don't
Yes.
mind, for those who wish to have certificates, to whom should they send the email? We can probably type it in the chat box. Or...
Okay. All right, I can. Okay, let me just share. Hold on, please. Let me just stop share, and then let me just share the our conference, upcoming conference, the 2022 for annual PAASE meeting symposium. Let me just share screen again. Can you see this now? Not yet.
Hindi pa po.
Okay, sorry about that. Let me just share. Here it is. Okay, can you see this now?
Yeah.
Okay, there you go. So this coming October 11 to 14, 2022, we are all inviting you to attend our 2022 annual PAASE meeting and symposium, or the 42nd APAMS. So we have this website. You can go through this APAMS 2022 at paase.org. And here's our call for papers. The deadline for the submission of abstract was extended. It will be now August 26. And this will be having notification of acceptance starting September 1st. And we also have an early bird registration deadline on September 15. Okay, so far we have our keynote speakers, National Scientist Father Nebres and former United Nations Special Rapporteur Victoria Tauli Corpus. And these are the schedule, but these will be details of this you can see through our website. And that's it for now. Sorry about that. And for the registration fee, it's 1,000 pesos. Is very cheap and affordable, but you will listen to a lot of speakers from not just from the Philippines, but from the States and other countries. And there will be different topics on science and technology and engineering and on education. We will have 15 parallel sessions during that 4-day conference. Again, thank you for attending this webinar. That's it.
Right. So, thank you po, Dr. Completo. So hopefully a lot of the participants here can consider joining the annual meeting on October. Just to follow up on Ma'am Gladys, for those who wish to get certificates, can we send them the email
yes.
to where they will um,
Okay, hold on. Okay, so and then also while I'm doing that, can we do a photo up, please?
sure. Sige po. I'll be the one to take the photo na lang. All right, so for those who can show their self in the in front of the camera, so kindly turn on your cameras. So there are 4 panels, so please just keep smiling while I take photos. All right, so first page. Wait, sorry. Okay, so first, all right, smile. Second page. Right, third page. Just keep smiling. Sorry. And the last page. Okay, so ako na lahat. So thank you very much. And
I gave the email
there.
address. Okay, so just be patient, please. We need some time to prepare the survey form, okay? And then, but once you send that email, okay, eventually by next week, all right?
Okay, so yun. So maraming salamat po. So kindly take note of the email address that Dr. Completo provided in the chat box for those who wish to get their certificates. All right, so that's acesancheta2@up.edu.ph. So so that's it for this morning's session. So thank you very much again for joining us. And we hope to see you over the next 4 Fridays for our Omics webinar. So maraming salamat and have a wonderful day for those in the Philippines and a wonderful evening for those in the US. So salamat po, salamat.
Good day. Good.
Thank you very much.
Thank you po.
Congratulations.
Congratulations, good job.
Thank you po. Thank you, Dr. Pen.
Dr. Lacerda.
See you.
Yes, Karen, visit us here in UPLB. Okay.
Ay, soon po.
Yes,
Very impressive. Very
That's-
impressive.
That's why
Congratulations.
I gave
Karen.
background.
Karen, advance happy birthday,
Ay.
right?
Thank you. Thank you po.
Karen, submit
Thank
a
you, Karen. Very
paper.
good. Thank you so much.
Submit a paper for the 42nd APAMS. Rap will nominate you. Ganun eh, Rap, I already
So yun na.
Okay po.
Lagyan
Thank
na
you po.
natin ito
That's
sa
it.
technology session. We need to put her on
Yes.
the technology session.
So Rap,
Yeah.
mag-nominate ka pa more from the LSU, ha, Rap?
Sige po, we'll do my best.
Okay, thank you
Great
very
job.
much, Rap.
Good job, Rap.
Thank you po, thank you.
Alright.
Thank you. Maraming
Sige,
salamat.
bye.
See you.
Thank you very
Bye-bye.
much.
Bye-bye po.
Bye.
Thanks, Karen. Bye.
Thank you, Karen.